Let's talk now about some fundamental principles for power electronics. So, like I said, most of you won't come from a power electronics background. Some of you don't come from an electronics background. So I think it's important that we cover some basic concepts here about the way we process electrical power, because if you don't understand those basic concepts, then it's much more difficult for you to look at specific circuits that we use in energy harvesting and really understand why we use them and why they're constructed in a certain way. Even if you understand now, and I hope you do, what the electronics that is linked to the harvester is supposed to accomplish, there are some basic principles with the way that we tend to build power processing circuits. And if you understand those principles, you'll understand a bit more easily why we construct those circuits in a particular way. So I guess the important thing here in terms of power electronics is that it is a different branch of electronics to what most people think of when they think of electronics. Mostly people think of electronics as being fundamentally something that is doing computations, something that is doing calculations, signal processing. People think of audio equipment, CD players, all this kind of stuff people associate with being electronics. But of course, actually, the thing that is keeping my laptop powered at the moment, plugged into the mains, converting the 230 volts in the mains at 50 hertz to, in this case, I think 18 volts DC for the laptop to run off. That's also a piece of electronics. But its function is not to process information. Its function is to process electrical energy and convert it from one form to another. And of course, the main thing that it has to do is to do that in the most efficient way possible. Any 230 volts AC that goes in terms of electrical power, we want all of that to come out the other end with very little loss in the middle, which is a bit of a different requirement in terms of information processing systems. Information processing systems, we're more concerned at the speed of processing, although we may, and are more, I guess, concerned these days with the power consumption of those systems being low, which is kind of analogous to making sure the efficiency in a power processing circuit is as high as possible. So if we think first of all about power electronics as a discipline, where it comes from, why it exists, well, a lot of this really comes down to wanting to do voltage conversion. And if you think about the way that voltage conversion has been traditionally done over the history of electrical engineering, then we use a transformer. If you look at the way that the electricity distribution and transmission grid is built, it's even today it's built on copper and iron of transformers. And because we have AC, and this is one of the significant reasons why we have an AC distribution system, we can use transformers. Transformers are incredibly efficient, and so we put them to good use in the electricity distribution system. Of course, in actual fact, one of the things that we're interested in doing now that we're powering electronics from the mains, a lot of the time is converting from AC to DC, and then we might want to convert DC voltage at one level to a DC voltage at another level. We don't only want to do conversion from one AC voltage to another AC voltage through a transformer, we're also interested in converting DC levels, because we might have batteries at one voltage that we want to power a circuit at another DC voltage. So being able to do DC to DC conversion, clearly that's not something that we can do directly by using a transformer. A transformer may actually, interestingly, be part of the circuit that accomplishes that task, but it is not a case of simply plugging a transformer in and getting a different DC voltage out. It doesn't work like that. So essentially we're interested then in building power electronic circuits. A significant part of the reason for doing that is to be able to do voltage conversion from one voltage to another, and also, as I've said, to do AC to DC conversion. And certainly, whilst that is something that traditionally has been analysed, particularly in the context of mains electricity, because I want to power my DC laptop from the AC mains that comes out of the socket on the wall, that's the same thing broadly that I want to do with an energy harvester. I need to take the AC from the piezoelectric material and I need to power a DC load. So this AC to DC conversion is something that also is very important to us here within the context of energy harvesting. Just to give you an indication of the scale of bits of power electronic conversion here, and traditionally where the subject comes from, because clearly applying this to energy harvesters is a very specific type of use of power electronics, a very valid use, but if you look at the total number of people internationally that would call themselves specialists in power electronics, probably less than 1% of those people would also consider themselves doing power electronics for energy harvesters. And traditionally, people are doing larger scale power electronics for things like wind turbines. Here's a power converter cabinet here. You might want to look in terms of the scale at this of something like a couple of 100 kilowatts in each of these two cabinets in terms of the sort of power density that you achieve. So if you look at the sort of power electronic converter that you see that is powering your laptop computer as being the small brick, then it's typically, you know, the order of 100 watts. Once you start to get power electronics above a few kilowatts, maybe approaching 10 kilowatts, it ends up being something that's in a box this size. Once you get into the hundreds of kilowatts, when we start talking about perhaps traction applications for electric vehicles or trains, or for things like interfacing with wind turbines, then you end up with building these things in huge cabinets. And it's a very different thing in terms of construction to what you see for information processing electronics. You're very used on standard pieces of electronics to think about the electronics as simply a PCB. It's a fully integrated thing on a PCB. It's very easy to manufacture, and it's, you know, more and more it's all on a single chip. With power electronics, because it fundamentally requires you to be storing and releasing energy from element to element, the thing has to be bigger. And it tends to be built, therefore, of larger discrete components, and it tends to be assembled more in this type of scenario in a bunch of cabinets, rather than all being on a single circuit board. But of course, it depends on the. So here's, you know, another example. This is a typical power brick for a laptop computer. And you can see here, it includes a transformer. We can talk a bit about that. But it includes, and there's some capacitors there, but there's also some electronics and some transistors in there. And of course, by power electronics, we mean specifically using silicon or silicon carbide or gallium nitride as electronics to process energy rather than to process information. This is, I think this is part of the hybrid drive system from something like a Toyota Prius. I think the orange-colored cables give it away as being a Toyota Motor Corporation part, and that part there on top is the actual bit of electronics that drives the electric motor. One of the things that you get used to also with power electronics, although on the scale, of course, for energy harvesting, this is not going to be the case, but on larger scale power electronics, which is very common, the individual semiconductor parts are big enough to throw across the room in a lecture if somebody's sleeping to wake them up. And this is, of course, something that you can't do now with modern information processing electronics. So this is a diode here. This is a thyristor. This is an IGBT, which is a type of transistor. This is a thyristor, I think, and this here is probably a half-bridge transistor arrangement. And you can see in relation to a 10-pence piece. So these parts are quite big. Of course, when we start talking specifically about building power electronics for energy harvesting, then these parts will again become smaller because the total amount of energy that we have to store in the system becomes a lot less. So what are we interested in terms of different types of power conversion? Well, the sort of thing that you're very familiar with and you use every day because you plug a piece of electronics into the mains is this AC input to DC output as a rectifier. And there are lots of different ways of building that. We'll certainly talk about this because whilst that's something that you do all the time when you plug electronics into the mains, it's also exactly one of the things that you want to do when you power an energy harvesting device, or a device from an energy harvester rather, because the harvester is almost always producing AC. You might want to do DC to DC directly because, as I said, if you've got a particular DC output on your harvester into a piece of energy storage, a capacitor or a battery, the device that you power from that battery might not want to work at the same voltage as the battery. So you might want to be able to do a direct conversion from one DC voltage to another. And actually, if we understand the basic operation of the circuit topologies that go from DC to DC, which we'll look at in some detail in the next few slides, actually at that point you broadly will understand most of the basic principles, the important basic principles for power electronics. If you understand DC to DC conversion, then actually understanding the other types of conversion in here is relatively straightforward because there's a whole bunch of basic principles to learn here. Once you've learned them in this context, you start to understand the other types of power conversion more easily. So these are the two that are the most relevant to us here in the context of building an energy harvesting powered sensor node. There are a couple of other different types of circuit topology that are in very common use in larger scale power electronics, converting from DC on the input to AC on the output, something called an inverter. And that is something that you might use to grid connect, for instance, a solar cell which is producing DC into the mains where you're wanting to export power into the mains. It's got to have DC input, AC output. Also for driving an electric motor, an induction machine, then you typically would require that to be an inverter-driven machine. You can do AC to AC as a direct conversion, and of course, earlier I mentioned to you that transformers is the very well-known way of doing this, and it's still a valid way of operating, even though it's obviously a very historic piece of technology. It's still very, very good. But it does require, and it does cause the input and the output frequencies to be the same. You can scale the voltages, but the frequencies are the same. If you want to do one AC frequency to a different AC frequency on the output, you can either do that by going AC to DC and then using this DC to AC inverter, or you can go directly from AC to AC and produce different frequencies with something called a matrix converter. But that's beyond the scope of what I want to talk about today. But just to fill in the whole box here, you can take DC as the input or AC as the input, and you produce DC as the output or AC as the output. But the two bits of conversion that are most interesting from an energy harvesting perspective is the rectification, taking the AC source, making a DC output, and then once we've got that DC output, converting that DC into the right voltage that we want to use to power our load, and that's then DC to DC conversion. And I think from the perspective of you understanding the basic principles of power electronics, DC to DC is a very good thing for you to look at because it really lets us sort of do some analysis, understand why the circuits are built as they are, understand the trade-offs, and once you've got that, actually looking at the way the other circuits are built is much easier for you to understand. So let's take this example then of DC to DC conversion, and let's think about how it would have been done maybe 30 or 40 years ago, and perhaps how it still is done if you buy a really precision voltage source. Perhaps some of the laboratory power supplies that you use in the lab will still be done like this because actually it can produce the best quality output voltage with the least amount of electrical noise. But of course it has disadvantages, and certainly this is not the circuit topology that you would expect to see in something like a laptop power brick because it simply wouldn't be efficient enough. So if we look at this here as a very simple way of trying to step down voltage here from 15 volts on the input to 5 volts on the output, and that might be a very common piece of power electronics for us to consider. Certainly as I said, my laptop computer in this case, I think it takes 18 volts on the input, which is fine. But of course the processor doesn't use 18 volts. The screen actually uses a lot more than 18 volts for the backlight on the screen. So clearly when 18 volts comes into the laptop, some of the voltage then, some of the power needs to be stepped up to a higher voltage, some of it needs to be stepped down to a significantly lower voltage. This is an example of a way of stepping the voltage down with here 15 volts on the input, 5 volts on the output. And hopefully you can see how that basic circuit is working. So we've got, in this case, a bipolar transistor here. Remember that we have a 0.7 volt drop across the base emitter junction on that BJT. So if we put a potential divider here made of a resistor and a Zener diode with a breakdown voltage of 5.7 volts, this voltage here is at 5.7, assuming we're in Zener breakdown. We connect that point there to the base of the transistor. So we've got 5.7 volts on the base of the transistor, 5 volts therefore on the output. So 15 volts on the input, 5 volts on the output. And as long as this point here stays at 5.7 because of the existence of this Zener and resistor arrangement, then we get our 5 volts on the output. So the circuit does its job, 15 volts in, 5 volts out. That was what we were trying to design. But we need to think very hard about the efficiency of this circuit and whether it's really a good circuit or not. So what's the total output power? Well, we're saying 2 amps here on the output. So our total output, 2 amps, 5 volts, 10 watts. The input power is the input voltage and the input current multiplied together. Now the same current here that's flowing in the output is also flowing in the input because that current's just going straight through this transistor. Obviously there's a little bit of base current. Let's assume that the gain of that transistor is high enough that the base current is negligible. Then we've got still 2 amps on the input, but we've now got 15 volts on the input. So we've got 30 watts on the input, 10 watts on the output. So of course our efficiency then is only 33%. And you can see that directly in this case, we're going from 15 volts to 5. The ratio of the conversion is a factor of 3, which is where we get this 30% efficiency, 33% efficiency from. So it's not a very good circuit. I mean, it does the job, it takes 15 volts, it produces 5 volts, but it wastes 66% of the energy whilst. And the reason it does that is effectively I've got 15 volts on one side of this transistor, 5 volts on the other, 10 volt drop across that transistor. That's what's doing the voltage regulation for me, but it's horribly inefficient. And that's no good. I don't want to be producing power electronic circuits for a laptop battery charger, for a grid-connected solar cell, for an electric car, for an energy harvester. For any of those scenarios, I can't work, really, with power electronics that is only 33% efficient. I want to take energy in at 15 volts, I want to dish it out at 5 volts, and I want to make sure that all the energy that comes in is available for use at the load. So the question is, how can I do that? Because it seems intrinsic in the way that I'm operating this circuit that I've got to drop voltage somewhere to go from 15 to 5. And if I'm going to drop a voltage across a component and there's a current through that component, there's going to be energy loss. So I need to do something that's a little bit more intricate, a little bit more inventive than just doing this type of voltage conversion. So incidentally, of course, so the power losses then, of course, are the difference, 20 watts. And it's quite important at this stage, I think, to realize why efficiency of these systems is so important. So from the perspective of something like, any battery-powered device, if it's an electric car, if it's a laptop computer, clearly any efficiency problems that you've got, any low values of efficiency in the system, is going to reduce the runtime of the system. If I've got a laptop and I'm chewing up half of the energy in processing the electrical energy before it even gets to the computer, then I'm reducing my runtime of my laptop by a factor of 2. Same argument with the electric car. Perhaps a slightly different argument in certain circumstances where I might already have high efficiency and I'm interested in getting the efficiency from maybe 98% to 99%. Doesn't make much of a difference in terms of the runtime of the system, but it might make a big difference in terms of the thermal dissipation of the system, how big the heat sink needs to be, and how I cope with that thermal management problem. And certainly depending, if I'm building a very small system, I want the system to be light. Efficiency will help me make it light because it means I can get away with a small heat sink. If you think then about the specific requirements for an energy harvesting device, actually the thermal management problems may not be significant at all because the power levels are so small. So if I've got 10 microwatts and I'm wasting 5, well, 5 microwatts is not really going to heat anything up. So it's not really a thermal thing. It's not really a problem in terms of wasting battery power from an energy harvester because the whole point was to get rid of batteries in the first place. So I've got a source and I'm taking power from that source. I'm passing it ultimately through my harvester, through my electronics, to my load electronics. I'm not so bothered about the efficiency from a heat perspective because there just won't be any heat. I'm not so bothered about my efficiency from the perspective there of the battery runtime because I've got an infinite amount of power in the source because I'm harvesting from the ambient. So why would I be bothered about the efficiency of a system in energy harvesting? Well, actually, it really just comes down to there's a certain amount of power you can pull out of the source based on the basic requirements and fundamental principles we saw in the last slideshow. And so if I can generate 10 microwatts as an absolute limit from a particular harvester, and my electronics is only 20% efficient, well, then I can only get 2 microwatts useful into the load, and I might need more than that. So the efficiency really from a harvester perspective is not about thermal management, it's not about maximizing battery runtime, it might be simply about making the device work at all. Because without efficient power electronics for an energy harvester, the total amount of power that's available in the first place is small, and you don't want to be reducing that by wasting it with this type of circuit. We don't want to be throwing away 66%, 67% of the energy by doing this. So the solution then is to operate the circuit in something called switch mode. So this circuit here is what we would call a linear regulator. And if you look at data sheets for electronics, if you build a piece of electronics, you'll see this. If you look on, if you look at RS or Farnell or Mouser or DigiKey, wherever you buy your electronic components from, you'll find big sections in their catalog for linear regulators. But this is a fundamental problem with this. If you do 15 to 5 volts, you've only got 5 divided by 15 times 100 of the efficiency. We'd like to be able to do this voltage conversion in a completely lossless way. We'll never make it completely lossless, but that should be the target. And this circuit can never do that. fundamentally. Doesn't matter how good we make that transistor, in this circuit topology, it's got to drop 10 volts. So how do we try and get away from that inherent loss when doing voltage conversion from one voltage to another? If instead we kind of think about operating this circuit, as I said, in something called switch mode. And this really comes from, there's a whole bunch of work that was done, I guess, back in the 60s and 70s. There's two guys that come up a lot when you look at early power electronics, a guy called Middlebrook and a guy called Chuk. And actually Chuk has put his name to a particular type of power converter. He's still alive and well and going around conferences. If you go to a power electronics conference and he's there, everybody wants to speak. Very famous guy. So they basically came up, and other people, of ways of processing electrical power from one voltage to another, in this case, as the same example, 15 volts in, 5 volts out, but not inherently making the efficiency 5 divided by 15. They built circuit topologies which let them achieve, theoretically, 100% efficiency. So how did they do it? Well, they simply realized that if you operate this transistor in a scenario where it's fully switched on, then there'll be no voltage drop across it. So in the previous scenario, the transistor was partially switched on. It had some current flowing through it, but it had a voltage drop across it. What they realized was if you operate this thing fully on, there'll be no voltage drop across the transistor, so, or very little voltage drop, so there'll be very little power loss. If you operate it fully off, then the same is true. There'll be no current, so there'll be no power loss. And so what they said was, well, I can get the voltage on the output here, I can get the average value of the voltage to be the voltage that I want, simply by pulsing this transistor on and off. So if I operate that transistor with a duty cycle 50% on, 50% off, then I'll get 7.5 volts on the output. If I operate it with a 30% duty cycle, I'll get 5 volts on the output. Now, of course, that 5 volts on the output is an average, and the instantaneous voltage on the output sometimes is 15, sometimes is 0. But the average voltage is correct. So I've got this set of pulses here that I'm putting into this resistor, as it is as a load at the moment. And I can actually get 5 volts average across that resistor by pulsing the transistor with no loss, or virtually no loss in that transistor, because it's either fully on or fully off. Now that's not good in terms of giving me a nice smooth voltage here. The resistor doesn't care, but if it was an electronic circuit, it would. And so I don't want to have this type of circuit, but this is an inspiration for how I can build a circuit. Okay, so what I'm basically looking at then is chopping between the two states, between the on state and the off state, and then I'm getting a voltage on the output, which is the average of those two states, depending on the amount of time spent on the on state and the amount of time spent in the off state. So in this case, you can see that if I operate on for 10 microseconds and off for 30 microseconds, then I end up with 5 volts on the output. Now, as I say, in principle, this can approach 100% efficiency because the transistor has nowhere now to lose the energy. It's either fully switched on with no voltage drop or fully switched off with no current. So how do I go about making a useful power supply from this principle? Well, I keep my original concept here of a transistor that I'm going to pulse on and off. So when it's fully on, the voltage across it is 0. When it's fully off, the current through it is 0. And I add, actually, a couple of extra components here. Well, actually, 3 extra components. I've got a diode, and I've got an inductor and a capacitor. And essentially, all I'm doing is now chopping the voltage at this point here, Vx. So Vin is a particular voltage. Vx is then a voltage which is a pulse, which is going between ground or Vin, as I turn that transistor on and off repeatedly. And then I've got a low-pass filter. So I've got basically a chopped waveform that I'm applying here at this point, Vx, going between 0 and Vn, and then I'm taking the average of it with a low-pass filter. So if I operate this transistor with a duty cycle of 50%, then I'll see a square wave exactly at this point with a duty cycle of 50, which I'll low-pass filter. So the output voltage at that point I would expect to be exactly a half of Vn. If I make that voltage, the duty cycle 25%, I'd expect the output voltage to be a quarter of Vn. But purely because while I'm operating this, that transistor is either fully on or fully off, there's almost no power loss. So when the transistor's on, the input voltage minus the output voltage is applied across the inductor. So there's a certain output voltage here. Think about how we analyze this now. There'll be a certain output voltage. When I turn the transistor on, I put a voltage on here. There's a smaller voltage typically on the output. This is a step-down converter, and we'll see why that has to be the case. And so current will build up in the inductor. Current will flow into the inductor. Current is going to rise, assuming that the voltage here is bigger than the voltage here. There's a positive voltage across the inductor, so that inductor current will rise. And it will rise linearly because it just depends on the voltage across the inductor divided by the inductance. Often when people talk about charging inductors or charging capacitors in electronics, they get completely used to saying that these things charge with an exponential rise or an exponential decay. That's not happening here because we've got a fixed voltage across that inductor. It means the current rises at a constant rate. So we store energy in the inductor, a half Li squared, and the capacitor current is then the difference between the inductor current and the load current. So there's some current flowing through this inductor here, some current is flowing through the load, and some current is flowing through the capacitor. And of course what we're doing here by chopping the operation of this transistor and putting a voltage in here which is a square wave, we've got a ripple current then on the inductor. Sometimes the inductor current is increasing, sometimes it's decreasing. So there's a high frequency current associated with that inductor current. Depends on the frequency with which we switch that transistor, but it tends to mean that the high frequency component of current there will flow through the capacitor because the capacitor is a short circuit for high frequency, and the rest of that, the DC current, will flow through the output path. So we've effectively got now a system which takes a DC input voltage, produces a DC output voltages via an AC part in the middle. So we're effectively going from DC to AC back to DC. But because we're doing that, because we're then able to operate this transistor fully on or fully off, we can achieve theoretically 100% efficiency, which we couldn't do before with the simple linear regulator. So if we look at the equations for this, so I've kind of already told you the answer, but it's good to work it through more thoroughly. So the basic way of looking at this circuit and the intuitive understanding is to say, well, this voltage here is either connected to Vn, because the transistor's on, or it's connected to ground because if this inductor is conducting, this diode is having current pulled through it, so this voltage is at 0. So when we switch the transistor on, Vx is at Vn. When we switch the transistor off, Vx is connected to ground. So depending on the duty cycle of the transistor, I've got an average voltage here of Vx, which is the duty cycle multiplied by Vn, and then I low-pass filter that, and so my output voltage should simply be the duty cycle of the transistor multiplied by Vn. And in a sense, that's kind of what I need to know about this circuit. It's able to step the voltage down from the input to the output, and it's controllable because I can set the value of delta on that switch. If we look at it in a bit more detail, because we can analyze this a bit more carefully, when the transistor is off, then the diode junction capacitance is going to be discharged. Voltage at this point here, Vx, is going to fall because current is flowing through this inductor, has to keep flowing because you can't instantly change the current in the inductor. So current now has to flow around this path instead during the off state. And of course, that means then that the inductor current is going to fall because now current is flowing from left to right, but this voltage on the left is now smaller than the voltage on the right, so the inductor current will fall. So it was rising in the previous case. Inductor current was rising here because this voltage was higher than this voltage. In this case, it's now falling because this voltage is higher than this voltage. And actually, that's how we get this system into steady state. When the transistor is on, the current in the inductor rises up a bit. When it's off, the current in the inductor falls a bit. If the rise in a cycle is equal to the fall in a cycle, then cycle to cycle, we're in steady state. Okay, so that's what the rest of the current flow does. We've basically got a loop now which is flowing while the transistor's off. The inductor current keeps flowing, high frequency components in the capacitor, and the lower frequency, whatever the load is. So we define two different types of operation for this type of circuit: continuous conduction and discontinuous conduction, and then there's the mode in the middle where we're on the borderline between those 2 points. So in continuous conduction, we're constantly increasing the inductor current a little bit when the transistor's turned on, and decreasing it when the transistor's turned off, then increasing it when it's on, etc., etc. And it's basically got a DC value of current flowing in that inductor with this small ripple on top, that is going up and going down. And like I said, if we're in steady state, the increase in current while the transistor is turned on has got to be equal to the decrease in current while the transistor is turned off. And so the average value remains constant. If we move into discontinuous operation, then effectively what happens there is we turn the transistor on, current builds up in the inductor, reaches a certain point, we turn the transistor off, back into this mode of operation. When we turn the transistor off, current is still flowing in the inductor, it'll flow around this loop, but it's decreasing. If we let it decrease all the way to 0, before we turn the transistor off again, we've got then potentially a period of time where the current doesn't flow in the inductor at all, then this is called discontinuous conduction. So in terms of the actual graphs showing us here how the circuit operates, then we apply a pulsed gate voltage here onto the MOSFET, going between on and off all the time. You can see here that we're operating with about a 30% duty cycle, which is what we were wanting to go from 15 volts to 5 volts. Yeah? So if you didn't have the low-pass filter, then actually this would be the voltage that you would see at the output, the voltage at Vx, which is this pulsed. It's changing between V in and 0, V in and 0. So the average value of that is the voltage we're after, but our circuitry wants a constant voltage. So we're powering a microprocessor or a sensor from our power processing circuit, and we've got to be able to do that directly from a smooth, nice, steady DC voltage like you get from a battery. So the voltage that we see at the output of the chopper, this bit here, is constantly going up and down. So we low-pass filter it so that we get the average value and we get a nice, smooth, hopefully a nice, smooth output voltage. Part of this is going to be designing this properly. If we don't design this low-pass filter properly, we won't get a smooth output voltage. So you can see here we're pulsing this transistor on and off. These are the gate signals. This is then the voltage that we see at Vx. And then you can see here the current that we get in the inductor. So the transistor is on, so the current is ramping up in the inductor, the transistor switches off, the current ramps down in the inductor, and the increase is equal to the decrease if we're in steady state, so we have an average output current here, which is exactly the current that flows to the load, I out. And the ripple current, the AC part, is what flows through the capacitor, because the capacitor is the thing that is the short circuit for high frequency. Okay. So if you look at the current that's flowing in the transistor and the current that's flowing in the diode, these are the shapes of current in the transistor and the shape of current in the diode, because when the transistor's on, it is clearly conducting the same current as the inductor. When the transistor is off, the diode is the thing that is conducting the same current as the inductor. So if you look at the actual current flow in the transistor, it's conducting this bit of the inductor current, but when it's off, it conducts nothing. And then the diode takes over, and the diode conducts this bit of the inductor current while the transistor's off. So you get this real switching of current flowing through one path in the circuit and switch it to flow through a different path in the circuit. And that's really inherent in processing electrical power. You're switching the way that current is flowing in the circuit from one loop to another loop so that you basically use that to either control a voltage by controlling how much of that current flows into a capacitor, or by controlling that current directly by measuring the current and changing the duty cycle and changing the path of that current to be able to control that current that's flowing in the inductor. So then the capacitor current is just the AC part of that inductor. Okay, so let's try and work out then formally what the output voltage of this circuit is going to be. I've already mentioned to you that basically you can think of that node Vx as being having an average voltage of the duty cycle multiplied by the input voltage. And if we obviously are taking a low-pass filtered version of that switched chopped voltage, then we would expect the output voltage to be just the duty cycle of the transistor multiplied by the input voltage. And that's a very quick way of describing how this circuit works. But we can do it a bit more formally as well, which actually is quite useful for analyzing the behavior of the circuit in a more formal way. So in steady state, as I mentioned to you, any increase in current during the on time of the transistor has got to be equal to the decrease in current during the off time of the transistor. Otherwise, we're not in steady state. So we can do this then quite simply with some very basic electrical engineering knowledge as to what is delta I in the on state. Well, it's just the on time multiplied by the rate of change of current in the inductor. So the on time is just T on, and the rate of change of current in the inductor is just the voltage across the inductor, in this case V in minus V out, divided by the inductance. So we've got a total delta I in the on state of T on times V in minus V out over L. Likewise, when the transistor is off, the voltage across the inductor is 0 on the left-hand side, and it's at V out on the right-hand side. So the voltage across the inductor is 0 minus V out. So it's just minus V out divided by L to get the rate of change of current. And so the total change is the rate of change multiplied by the off time of the transistor, or the conduction time of the diode, T diode. If we then equate these two things, or basically actually we add them up, we say delta I on plus delta I off has got to be equal to 0. If we do it that way, it's easy to get the signs correct. In other words, the total change of current over a cycle in steady state is 0. We can just add those two things up. So we add this expression and this expression, equate it to 0, and we can then work out V out over V in is T on over T on plus T diode, which gives us exactly what we're expecting. V out divided by V in is equal to delta. So we've got now a way of processing electrical energy from one voltage to another, as long as the output voltage is lower than the input voltage, where we can do it in an almost lossless way. Fundamentally, it can be lossless. It's only the practical implementation that makes the losses present. And we can control that depending on the value of delta. So if I want the output voltage to be equal to input voltage, I just set delta to 1. If I want it to be 10% of the input voltage, I set it to 10%. So it's a nicely controllable supply, and it's beautifully efficient. The previous supply, the linear regulator, that had losses that were not just about the implementation. The losses were fundamental to the approach. So that basic principle of taking this type of circuit, creating an AC waveform by switching this device fully on, then fully off, then fully on, then fully off, and low-pass filtering it, is what gives us this capability of power processing in a lossless way and convert one voltage to another. Okay, does everybody understand the basic principle there? Because that's really fundamental to everything that we do in power electronics. It's one circuit topology. There are lots of circuit topologies, but this basic principle is key to all of these circuits. You only operate a transistor in power electronics fully on or fully off. If it's fully on, there's no voltage drop across it, so there's no power loss in the transistor. If it's fully off, there's no current in it, so there's no power loss in the transistor. If you're going to do that, operate between fully on and fully off, you end up basically creating square waves, high frequency square waves. And that's not what we want from the perspective of a piece of load electronics. So we basically take our DC input, we create a high frequency square wave, and then we filter it. And that's what gives us our DC output. Because we're operating the transistor in this so-called switch mode, fully on or fully off, the circuit can in principle be lossless. Okay, does that make sense to everyone? If we operate this device in discontinuous operation, as we showed earlier, so we just did the calculation here for continuous mode of operation, where we said the increase in current in one cycle has to be equal to the decrease in current while the transistor's off. And that was how we calculated, via this volt-second balance across the inductor over a cycle, we calculated this transfer ratio. If we operate in discontinuous conduction, we have a slightly different set of graphs here. Transistor again going from on, off. While the transistor is on, then of course Vx, the point Vx, is equal to Vin, as it was before. When the transistor is off and the inductor has got current flowing in it, the diode is pulled into conduction, and that means that Vx is held at 0 volts, or just actually slightly negative, one diode drop below 0. But when the diode stops conducting, when the inductor current falls to 0, Vx at that point, if that transistor is turned off and that diode drops out of the circuit and there's no current in the inductor, then the point Vx is just equal to V out at that point. So we were previously having, in continuous conduction, that point was purely defined as either being at V in or being at ground. When we go into discontinuous mode, it's either at V in, ground, or V out. So when there's no current flowing in the inductor, that point there is going to be held at V out, which is exactly what you see here. The transistor is on, Vx is at Vn, transistor switches off, diode comes into conduction, pulls Vx to 0 until the current in the inductor goes to 0, at which point the point Vx shoots up to Vout, stays at that point until we turn the transistor on again, when the voltage goes back up to Vn, and at that point, of course, the current starts ramping up. So similar sets of waveforms here for the current that you see in the transistor and the current that you see in the diode. Bit different in terms of the operation though, because now the current in the inductor is able to fall to 0 during part of the cycle. We can do a similar sort of analysis here for discontinuous operation to calculate what the output voltage is, and it's a little bit more complicated now than what we calculated previously. So before we had this nice linear relationship, which actually was very useful also if I come to putting a closed loop controller around this power supply. If we could operate it in its continuous mode, where we've got V out is equal to delta times Vn. Delta is the thing that I'm going to control the plant with. It's a linear plant. It's very easy to design a controller for it. Once we drop into discontinuous mode, I've now got to basically calculate the area of the total amount of charge that gets moved through this system and the amount of total energy that comes off the capacitor, keeping the output voltage constant. So I can do that calculation, and I get a rather more complicated expression here for the output voltage divided by the input voltage when I'm in discontinuous mode. And you can see now that it is not simply that nice relationship where the output is delta times Vn. It relies on Vn, but it also relies on the frequency of operation, the specific value of inductor, the amount of current that's flowing, etc., and the square of the duty cycle. And what actually happens there is that the voltage, as you start to decrease the load on these systems, as you go into discontinuous mode, the output voltage tends to fly up. So you need to be very careful. So one thing that does not happen with the previous circuit we looked at, the linear regulator, it's lossy, but it's very simple to control, and it will never do this sort of behavior. Once you move into switch mode circuits, then in this case, it has two modes of operation. If you're in the first mode, it's very easy to understand, very easy to control. You move into the second mode here, it's a little bit more difficult, so you have to be a bit more careful. Okay, in discontinuous mode, the boundary between continuous and discontinuous mode, exactly where the current reaches 0 here at this point in the inductor current, just as we turn the transistor on again. And you can calculate, of course, then if you use this expression to calculate the output voltage, or you use the other expression, you'll get exactly the same answer. So, looking at this then in LT Spice, which you're now all hugely, yes? So for this type of converter, not so much. What will tend to happen is you might be volume constrained on the size of the converter, and so the biggest consumer of volume probably is going to be the size of that inductor. And so if you're constrained with volume for this converter, you would make the inductor smaller, and making the inductor smaller might mean you end up in discontinuous mode. So you could make something that was more compact probably in discontinuous mode, and the trade-off is that the control is a bit harder. When you look at other circuit topologies, there's a circuit topology, a common circuit topology called an isolated flyback converter, which uses a transformer core as the energy storage mechanism. It's very common people design those in discontinuous mode to minimize the size of the core and to minimize the cost. So actually that type of power supply is used very often in pieces of consumer electronics like DVD players, Sky set-top boxes, that sort of thing. Will typically have a flyback converter. It'll typically be operating in discontinuous mode because cost is such a huge driver in making the power electronics for those things that if they can shave 20% off the volume of the core, they can save 20% of the cost of the core. So, okay. So if we look now briefly at putting this into LT Spice, you can see we've got a switch here, our MOSFET. It's being commanded here via a switched voltage source. There's a diode here. Here's our filter, inductor and capacitor. And then we've got a whole bunch of different loads here that we can switch in and out depending on what load we actually want to be connected here. So there's actually one of the other things that you notice is that there are actually two different capacitors here. And this is something that from a practical perspective, once you start building electronics, even building power electronics for energy harvesters, you have to be very careful about. So there's a high frequency capacitor here, 100 nanofarads, which looks pretty well like just a capacitor. But there's another capacitance here, 50 micro, much bigger, probably electrolytic in nature. This one may be a ceramic capacitor. This is probably electrolytic. And so an electrolytic capacitor, unfortunately, is far from being a perfect capacitor. If you put a square wave current into a electrolytic capacitor, you won't see a integration of that into the voltage. Because in actual fact, it has reasonably significant self-inductance and probably reasonably significant resistance as well. And so the voltage you see across that capacitor will not be as small as you expect it to be. So here's what we get if we look at the SPICE simulation of that supply. So we've got an output voltage and an input voltage here. So the output voltage delta times Vn is pretty much what we expect in blue. This is what we expect to have here, exactly 5 volts based on delta times Vn. This is what we actually have, which is a little bit less. We'll talk in a moment why the target voltage that we achieve is a little bit less than the voltage that we actually wanted. And you can see the waveforms here, basically doing exactly the sort of thing that we wanted to do. The transistor's turning on and off with a 30% duty cycle. You can see the inductor current ramping up while the transistor's on and ramping down while the transistor is off. We then have voltage ripple that we see across the output capacitance here. And the interesting thing is the shape of that voltage ripple, because it is not purely integrating, as you would expect, the AC component of the current, because that's what a capacitor should be doing, integrating the current to give you voltage, because in actual fact, I'm putting now a triangular shaped current into a branch here, which is not just a pure capacitor, it has a resistor and an inductor. Purely because I can't build an electrolytic capacitor that is a perfect capacitor. It has those parasitic components, and if I put high frequency currents into it, then I will have to see those high frequency components coming out into the output stage. If I operate in discontinuous mode, things look a little bit more messy. So this, broadly speaking, in terms of the continuous mode of operation, behaves as I expected. The output voltage is a little bit less than I expected, but not by much. The currents are ramping up and down as I expected, in straight lines, as I would, exactly as I would expect. And there's a little bit of ripple voltage on the output here, so I was trying to make exactly a 5 volt output. What I'm making is something that's a bit less than 5 here, about 5.4, 5.5 volts on the output. And it's not quite perfectly holding at exactly a DC value. You can see there's a little bit of ripple on top of there, and that's because I'm not filtering this thing perfectly with that LC filter. And part of the reason for that also is that the LC filter itself, the C in that LC filter is not a perfect C. It's got some parasitic components associated with it, and that is then basically showing through in the behavior in the output. But it is essentially doing exactly what I think it should be doing. Not quite perfect, but very close. Unfortunately, when I start to look at what happens here when I move into discontinuous mode, things are a little bit more messy. And I've got broadly the right behavior here. You can see that the current ramps up when the transistor's on, ramps down when the transistor's off, stays at 0, almost 0 for a while, and then when the transistor comes on again, the current ramps up. So the current is doing broadly what I would expect. The output voltage here, you can see now, is higher than I was expecting. If I do the delta times Vn, I'm expecting 5 volts on the output. Now I'm getting above 5 volts, and this is what I said to you earlier. When you move this from continuous into discontinuous mode, the output voltage tends to rise above where you would expect. So this voltage here actually is the one that is calculated by this formula here, just not the one that is calculated by this formula here. So you have to know what mode you're in to know what voltage you expect on the output. The other interesting thing is this funny oscillation here. When we looked at the behavior of this circuit here, these are the kind of idealized graphs, and we're comparing these to what we see on these simulations. We expected the voltage node Vx to go from Vin when the transistor's on, down to 0 when the transistor's off and the diode is conducting, up to Vout when the current in the inductor drops to 0 as part of this discontinuous mode of operation, and then back up to Vin when the transistor turns on again. We see something nasty happening here rather than exactly what we would expect. So we see the transistor on, we expect Vx to be at Vn, transistor turns off, inductor current is flowing, voltage is pulled down to 0, that's correct. Clearly when the transistor turns on again we get the right behavior, but in between there we see these very interesting oscillations, and what we were expecting was that voltage to simply go up to Vn, be constant, and then go up again when the transistor turned on. Instead of being constant, we get these oscillations. And these oscillations actually come from a ringing between the main inductor in the circuit and the parasitic capacitance on the PN of the diode. And that is potentially also leading to a little bit of extra power loss. It's also potentially bad from the perspective of electromagnetic interference. So a circuit here, this is just an example of how when you build a piece of power electronics, if you look at how the circuit should work and you look at how the circuit ends up working, there's often these additional bits of stuff here that you might not be expecting to play a role that end up playing a role. So we've basically unintentionally, we've excited a resonance here between the diode junction capacitance and the main inductor in the circuit. And at first glance, when you look at the circuit, you probably wouldn't see that as an operating mode. But it's something that you should try and avoid if you can, this oscillation, because ultimately that's very high frequency and it's going to potentially cause problems with EMI. Just to talk a little bit more about the output voltage ripple that we see, as I've said, we've got a current here that is flowing in the inductor, which is ramping up and ramping down, ramping up and ramping down. That's inherent in the operation of the circuit. We'd like to be able to produce a perfect DC output voltage here. But if we're going to produce a perfect DC output voltage, we either need an infinite value of inductor so we get no ripple current, or an infinite value of capacitor so that we can put as much ripple into that as we like and not see a change in voltage. In reality, we are going to see some change in voltage because that inductor is going to be a finite size, as is that capacitor. And in addition, as I mentioned, that is not going to be a perfect capacitor, so any additional current that goes into a series inductance or a series resistance in that device is going to give you some ripple current that you want to try and avoid. Okay, so we can calculate, we can basically integrate the total amount of charge that gets pushed in and taken out of that capacitor, that area there, integrate that on that capacitor and find out what the voltage of that capacitor looks like. If it's a pure capacitor, it will look something like this. So we can fairly easily then, by integrating that, find the total amount of voltage ripple that we expect to see on this type of power supply. Depends clearly on the capacitor. If I make the capacitor bigger, then the ripple voltage will go down. If I increase the frequency at which I switch the transistor, the ripple voltage will go down. If I make the inductor bigger, meaning that my delta I, that ripple current that I'm getting in the inductor, that will go down, and it will also decrease the ripple voltage. So inherently, I've got a circuit topology here which is inherently much more efficient than the linear regulator circuit, but clearly has quite a few more quirks than the linear regulator. This requires me now to have a small voltage ripple on the output. On the previous circuit, I could get something that was dead level, perfect DC output. This one is almost a perfect DC output, but with a small ripple on top. And if I operate the circuit at higher frequency, or I put a bigger capacitor or a bigger inductor in, I can reduce the value of that ripple, but it's always going to be there. So as I mentioned, the capacitor that we put in there is probably, at least on power converters that get to be over a few watts in size, and I appreciate for energy harvesting, maybe this isn't going to be a problem, but it depends how small we need to make the harvester. We're probably going to end up using some form of electrolytic capacitor somewhere. The electrolytic capacitor is really relatively poor quality capacitor because it has potentially significant capacitance, but also fairly significant series resistance and series inductance. And if you put a current shaped like this, as the AC current from our inductor ripple, into these three components, okay, so the capacitor is integrating this perfectly. That's what you get when you integrate it. The resistance is giving you a voltage across it which is proportional to this. But unfortunately, of course, the inductor is taking the derivative of this and giving it a square wave. And the overall voltage that you see, therefore, across a capacitor that you expect to be a capacitor is actually the sum of the voltage across three separate components. And so it's not as good as you think it's going to be. Okay, so that is most of what I want to say about the overall principles of operation of this type of power converter, that step-down type of power converter is called a buck converter. Buck is the American terminology for reducing something, which is exactly what it does. And I mentioned to you several times that theoretically this device can be 100% efficient because there is no room for conduction loss in the transistor because it's either fully turned on and therefore there's no voltage drop across it, or very, very small voltage drop across it, or it's fully turned off and there's no current, and consequently the device operates incredibly efficiently. In actual fact, of course, the thing is not perfect when it's switched on. There is a small resistance in the transistor, so there is a little bit of energy loss. When it's turned off, there might be a small leakage current, but also when that transistor transitions from the on state to the off state and back again, it won't do it instantly. We try to make it switch very quickly, and I've been talking about producing square waves here. And of course a square wave is kind of really showing us that we move perfectly from one state to the next state instantly. But that's not going to be the case. The transistor takes a certain amount of time to turn on and a certain amount of time to turn off. And any time we've got voltage and current across and through a semiconductor at the same time, then we have power loss, and we can integrate the power loss to get energy. And we can then, of course, calculate the average power in something. So if we look at the power loss in this type of circuit, and again, this is something that's a very, very common way of calculating power loss in all power electronics. So I'm doing it here, showing it in the context of the circuit we've just looked at, but this power loss calculation is something that you can use for almost every circuit topology in power electronics, including anything that you come up with for piezoelectric harvesters. Then effectively I've got, while the transistor is on, as I've said, very little voltage drop across the transistor, current is flowing through the inductor. When the transistor turns off, current flows through the diode, and no current flows through the transistor. But there's a finite transition time between the transistor being on and the transistor being off. And the question then is, how does it make the transition from one state to another? Can I quantify how fast that transition is? And then can I calculate the power loss associated with that transition? So remember, when the voltage across the transistor is almost zero because the transistor is fully on, there's effectively no loss in the transistor. When it's fully turned off, there's no current in the transistor, so there's no voltage, there's no power loss in the transistor. But as it transitions from the on state to the off state, there will be a condition where there is some current in the transistor and there'll be some voltage across the transistor. So the transition period is crucial for understanding how efficient this circuit can be. So if we look at the behavior of this circuit, it's quite an interesting, quite a specific circuit, but it is the switching cell that you see in pretty much every piece of power electronics that has ever been used. So we have current flowing through an inductor, current is being pulled out of this node, and the current is either split between the transistor being on and current flowing through the transistor, or the transistor and the diode's on and current's flowing through the diode. And we've got to basically look at what happens with the transition between one and the other. Well, if we think about it here, that inductor current during the time of switching between one state and the other is effectively going to remain constant. Current in an inductor does not change very quickly, and we're talking here about being able to switch from the on state to the off state in maybe 10 to 100 nanoseconds. Depends on the size of the devices, depends on the power rating of the system, but we would expect to be doing that probably in tens to hundreds of nanoseconds. So that over that period, we'll assume that this inductor current is constant. Now let's take the case where the transistor is switched on. Current's flowing through here, round a loop, through the transistor, through the inductor. The moment that I start to switch that transistor off, then think about what's going to happen. I'm going to try and reduce the current that's flowing in that transistor. But I can't reduce the current that's flowing in that transistor unless some current starts to flow in the diode, because the current into the inductor is constant. So if I've got a constant current flowing out of here, if I want to reduce the current in the transistor because I'm turning it off, and then commutate that current into the diode, so the diode current's going to increase, that's ultimately what I want to do. But I can't do that unless the diode itself is able to conduct some current. And if the diode diode is able to conduct some current, what does that imply about the voltage at this node? It's got to go towards 0, hasn't it? In fact, it's got to go slightly below 0 to be able to turn this diode on. So before I can even start to move some of this inductor current out of this transistor into this diode, that voltage has to collapse. It has to go all the way to 0 and slightly below in order to pull that diode into conduction. And even before it reaches 0, if it's just slightly above 0, that diode is switched off. But now that transistor has actually got the full voltage V in all the way across it. So my switch mode circuit, which was operating beautifully with the transistor fully on and no voltage across it, or the transistor fully off and no current through it, and therefore theoretically an efficiency of 100%, now I start to look at the detail of the transition of moving the current from this path to this path, and suddenly I figure out that I could only commutate current from this transistor into this diode if the voltage at this point goes all the way to 0 first, whilst the full current is still in that transistor, even before I've moved any current into this diode at all. So that's fundamental. It means that I've got to have some switching loss. When I translate the switch from the on state to the off state, that switch at some point during that cycle supports the entire input voltage across it and the entire inductor current at the same time. So while it's in transition, there is a significant power loss in that switch. And that's exactly what you see in these waveforms here. You see the voltage across the transistor as I go from the on state to the off state. You see the voltage across the transistor falling. You see the current rising here in the diode before the voltage across the transistor can turn on. What I've just been talking about was turning the transistor off. And before the current in the transistor before the current in the transistor can turn off, I've got to have the voltage across the transistor rising, which refers to the point Vx falling from V in to 0. So the voltage has to rise, and then the current can fall. So I've got these kind of overlapped areas here where I've got some current and some voltage across and through the transistor at the same time. So there's an inherent switching loss associated with these types of power converter, which effectively means that as I switch the device on, I get a sudden amount of energy loss, a sudden burst of energy loss, then a small amount of loss continuously as the transistor is conducting, but it's not a perfect conductor. It's got a little bit of resistance, so there's a little bit of loss there, and then when I turn it off again, I get another blip of power loss. So this is not quite what I was telling you originally, where this is theoretically an infinite efficiency circuit. It's fundamental now to the way that current will translate from one component to another, that there is a loss associated with that switching mechanism. There's a blip of energy when I switch in one direction and a blip of energy when I switch in another direction. And if I integrate that instantaneous power loss here over time and I see energy loss building up, there's a sudden loss increase there during the turn on state, a little bit of an increase while the transistor's on and looking like a pretty low valued resistor, and then another blip of energy there as I turn the device off. So clearly the losses in the system depend on the frequency. If I go to too high a frequency, that transition from the on state to the off state will be happening very frequently and the system efficiency will drop. But there are other trade-offs, as we already mentioned. If I want to have a small value of inductor, physically small capacitor, then there's a push to want to move to higher frequency. So again, there's a whole bunch of optimization here to start thinking about where exactly do I want to pitch my design. So if you want to look specifically at what the energy loss is going to be, then actually you will, yikes. Then you can look up these values typically on a data sheet. So when you're designing a piece of power electronics, and this goes for anything from a large-scale converter for electric train all the way down to designing something for an energy harvester, look at the data sheet. You need to know the loss values on the data sheet to be able to design this system properly. So the main design criteria that we might have, and thinking specifically here about the piece of power electronics that sits on the output of the energy storage element and powers whatever device is connected on your wireless sensor node, then you're going to be interested, of course, in making that as high efficiency as possible. You're going to be interested in the cost if you're doing large volume manufacture. You might be interested in having a well-regulated output voltage and a control loop to do that. Short circuit proof, if something goes wrong with the load, you might want to make sure that it doesn't damage the device. And you want it to be reliable and have a high mean time between failure. So just to give you a very quick walkthrough of how you would design this type of power supply, you know the specifications for the input and output voltage, you know the specifications for how much power you need to be processing. First of all, you choose a transistor that can cope with the right current and voltage. Choose a switching frequency based on that transistor. Certain transistors will be happy switching at high frequency, certain transistors will not, and that will be something that you can probably calculate by looking at the data sheet and seeing how much switching loss you will have. Once you've done that, you can choose the L and C values to get the right sort of voltage output quality that you want. If you make the capacitor or the inductor too small, you'll have a ripple voltage on the output. You can tolerate a certain amount of ripple voltage, but not too much. Okay, so principal constraints on the design ultimately are going to be things like how much voltage ripple, how much current ripple you can tolerate, and how much temperature rise you can tolerate. And the latter one of those, temperature rise, is probably not going to be an issue in energy harvesting. It's the one constraint here that you can relax. Okay, so the components. I already showed you this picture earlier of a bunch of different power semiconductor devices. So transistors, diodes, etc. In this case, that are designed for handling energy rather than for processing information. We're really going to be concerned here with using MOSFETs. At this sort of power processing level for energy harvesting, almost certainly you will be using MOSFETs. Never use BJT, bipolar transistor, in power electronics. It's almost always a bad move compared to using a MOSFET. Going up here to much higher power applications, then the different devices tend to be used, but of course that's really out of scope for what you guys are interested in. You may, however, and there are certain circuits that we have built where we've found tiny thyristors which have been very beneficial for some of the circuits that we've been using on the piezo devices, and I'll show you a little bit of that as well. But for most of what you do, you'll be using MOSFETs for power processing at these power levels. Heat sinking, I'll probably skip that because actually, as I keep saying, it's not really very relevant from the perspective of an energy harvesting device. If you do want to design a piece of power electronics with a heat sink, then the design flow is fairly straightforward. You work out the total losses in the system, and then you build a thermal model from the transistor all the way through to the ambient and figure out what the thermal resistance of the heatsink needs to be in order to keep the transistor at the right operating temperature. And you can do that with a thermal equivalent circuit. It's a very straightforward calculation. If you ever want to do that, like I say, you can look that up. It's fairly straightforward. In terms of designing the passive components, and this goes for anything at any scale in power electronics, then you need to look at basically choosing the cutoff frequency of the output filter. Make sure that you are operating well within so that the switching frequency of the transistor is well above the cutoff frequency of that second order output filter. So if we look at a very specific example, 48 volts in, 15 volts out, in this case an example of 10 amps, far in excess of what you would expect for a typical energy harvesting device, but the principles are the same. Then we first of all might look to find a MOSFET. Now this MOSFET here is quite a well-known MOSFET, power MOSFET, an early power MOSFET by a company called International Rectifier, IR. They no longer exist as a company. They were bought by Infineon a few years ago, but a range of MOSFETs that's very well known to power electronics people. That has a whole bunch of characteristics associated with it. One of them there, you can see the turn on and turn off energy loss, which you could then put into your calculations for designing the heatsink, but we're not going to bother with the heatsinks. So we would then also look up what we could do in terms of the output capacitance, because as you remember, the output capacitor is not a perfect capacitor. It has series inductance, series resistance. I need to be aware of that because I'm going to calculate the voltage quality on the output of this switch mode supply. And so I need to know what values I've got of parasitics in that capacitor to understand just how good the voltage quality is going to be. Okay, so effectively then it is a question of understanding the components, understanding how the components are not perfect, calculating the voltages, that you get because of those non-perfect components, and a trade-off between pushing the frequency high enough to make sure that the converter is small enough and the voltage quality is good enough, but not too high that the losses become too high and the system gets too hot in a large system, or too inefficient in case of an energy harvesting system. So I won't work through any more details of that particular example, but hopefully that gives you enough of the sort of basic physics background if you wanted to design this type of power supply, the basic principles of operation and the basic design choices that you need to make. There are other types of circuit topology that are very useful also in harvesting. There's a step-up type of power converter here, works essentially with the same principles as the one we just looked at, but puts the components down in a slightly different order. And you can see here that we have an input voltage on the left and output voltage on the right. We turn on the MOSFET here and we build up current in the inductor. We then turn the MOSFET off. That inductor current keeps flowing, can't go through the MOSFET because the MOSFET's off, pulls the diode into conduction and pushes the voltage up on the output capacitor. So this converter is able to have an output voltage which is bigger than the input voltage. The previous converter was the other way around. This one requires the output voltage to be greater than the input voltage. So there's the current path in the on state. The current path in the off state, the current path in the on state, we build up current in the inductor like this. Okay. So, same argument as before. When the transistor's off, the diode is brought into conduction. That current must flow in the inductor. It flows around the output loop. High frequency components flow in the capacitor. DC components flow in the load. And the voltage across the inductor is such that the inductor current is decreasing. When the transistor is in the on state, the current in that inductor was increasing. So we use exactly the same argument that we used before to calculate the output voltage for this converter. We say that during one cycle, the increase in current in the inductor when the transistor's on has got to be the same magnitude as the decrease in current when the transistor's off. We work out exactly the same way as before, but the equations are different now because the circuit connectivity is different. And we therefore get an expression for the output voltage divided by the input voltage of this converter is now 1 by 1 minus delta. So you can immediately see if the duty cycle of the transistor is 0, the output voltage is equal to the input voltage. As I start to increase the cycle above 0, then the output voltage rises above the input voltage. And of course, if here I take the duty cycle to a value of 1, then in theory the output voltage rises to infinity. Of course, the losses in the circuit mean that that cannot be the case. That you can also calculate an equivalent expression for the output voltage in discontinuous mode as well. Okay, maybe that's a little bit too detailed for what we're doing at the moment, and likewise, the specific calculation here is perhaps too detailed, but you can appreciate that again, because I'm putting currents into the output capacitor of this device that are not continuous, I expect, and it's an inherent part of all these switch mode circuits, that I do not have a perfect voltage. I'll have a small ripple voltage on top of a DC, and the trade-offs as to how small you want to make that and how fast you want to operate the converter, how big you want to make the passive components will all be determining the quality of the output voltage. Just to do a quick comparison between the first converter we looked at, which steps voltage down, and the second one, the boost converter, which steps voltage up. They all have essentially this fairly nice relationships between input and output. V out equals delta times V in for the buck. V out is 1 over 1 minus delta times V in for the boost. So you can see this one can step voltage up, this one can only step voltage down. There are then some subtleties in terms of whether the voltage ripple is large or small. And the voltage ripple on the output for a boost tends to be worse than it does for a buck, because in this system, typically you've got a fairly smooth current here in the inductor, which has got some ripple on it, but it's generally a smoothish current feeding the output. That's not the case here. The smooth current is on the input, and you're sometimes passing that inductor current through to the output. Sometimes you're not. Sometimes you're passing it just through the transistor. So you're putting basically chunks of energy out into the output here, whereas here you're putting much smoother flows of energy into the output. And that means then that for the same size of output capacitor, actually has a better quality output voltage than this. So again, it depends how sensitive whatever your load is here as to how much the voltage ripple on the output is going to play a part. And then you can control the output voltage of these devices by measuring the output voltage, feeding it back, and changing the operation of the gate drive here. So if the output voltage, if you start drawing current from this device, the output voltage drops a bit, you'd measure that, you'd feed it back into a control system, and you'd compensate by increasing the duty cycle a little bit to make sure the output there remained constant at the value that you wanted. I'm just conscious of time, so I won't go into the specific details of how you implement that. But I will talk briefly now about rectification, and then we'll talk a little bit more specifically about some circuits specifically for energy harvesting. So rectification, this is a circuit that you are probably very, very familiar with. As I mentioned, it's of limited use for lots of energy harvesting approaches because the voltage that you typically get from your transducer may be very low. You won't be able to pull these diodes into conduction easily enough. And so we've got to think probably about better solutions to doing AC to DC conversion than this circuit. But it's a very well-known circuit. It may be used, as I mentioned earlier, as a way of starting a system up from cold because this system doesn't require any control. You put in a DC waveform here, you'll get some DC voltage on the output. And of course, the basic behavior of the circuit is very simple. You simply get the positive values of the input, taking the absolute value of the input voltage, and you see that on the output. Okay, what you would typically do is add a capacitor to the output of this. This circuit here is shown with just a resistive load. Typically you add a capacitor in order to get somewhat DC values on the output. That then gives you an additional problem, and this is very relevant to energy harvesting. So what I'm often interested in with the harvester, if it's an electromagnetic harvester, let's take electromagnetic as the example, and I put a bridge rectifier on it, and I put a capacitor, and I might put a bit of smoothing inductance as well, in the same way that I was doing with the switch mode power supply, to get the best smooth DC voltage here on the output that I can. The problem now that I've got this output filter on here means that I'm only going to be drawing current from this waveform at the peak of the voltage. Because when I'm away from the peak, these diodes can't come into conduction. As soon as I put this capacitor on here, I make something called a peak rectifier, so that I only pull pulses of current from the voltage source, as you see here, at the peaks of the voltage waveform. And with the typical harvester, what I was wanting to try to do with the electromagnetic harvester was a set of waveforms which gave me a nice smooth set of forces, so that I had this nice linear damping. I wanted to ultimately have a force which was proportional to velocity. That's how I did all the analysis, and I wanted to then to be able to control that force so that the force was proportional to velocity and I could dial in the constant of proportionality. Well, I can't do that with this circuit because now it pulls a current from the harvester only at the peak of the waveform. So I've lost that nice linear relationship, and I've got just peaks of current that are flowing. So that's probably not very good in terms of operating the harvester in the nice linear mode that I was expecting. Okay, I've already shown you, I'm very conscious of time, I've already shown you this energy harvester and how we optimized it in the previous set of notes. And we said that we were trying to keep for this rotating harvester sine theta equal to 1, so we try and hold the mass at 90 degrees. How do we go about doing that based on the electronics that we've just looked at? Well, it's actually fairly straightforward now. You've just seen these switch mode power supplies. This is the boost converter, the second of those switch mode power supplies that we just looked at. I said to you on numerous occasions, things we can control in power electronics are voltages on capacitors. That's very useful for a power supply to be able to control the output voltage of whatever we're supplying something to. The other thing is controlling a current in an inductor. And there we are. On the input side of this converter now, we can control the current in that inductor. So we could measure that current, and if the current needs to be bigger, we increase the duty cycle of the switch. If it needs to be smaller, we decrease the duty cycle of the switch. So now, for this very simple rotating harvester, where I'm trying to hold this mass here at 90 degrees, I can do that, can't I? Because I can now measure the current on the input, and I can control the power supply to control the current in this inductor so that that current is exactly what I want it to be to control this mass to be at exactly the 90-degree point. So there's the first example, really, where I'm showing you that I can take a piece of power electronics. You have some basic understanding now of how that power electronics works. I can control the current in the inductor of the input of that power electronics. That then controls the force on this harvester and maximizes, if I've set it up properly, the total power that I can generate. Okay, let's not look at the specific details. There's an example of this device working, spinning around. You can see the offset pendulum, and we built actually a self-powered tachometer using this system. Okay, if we were to talk instead about a typical vibration-driven harvester, then we've already said passive rectification solutions aren't necessarily very good because I can't control the current very well. Instead, what I probably want to do is to use something that looks a little bit like a full-wave rectifier, but I replace two of the diodes with two transistors. This now, if you can see it, and it might take you a little bit of time after this lecture to look at this circuit, but this circuit now with the inductor, these two diodes and these two transistors actually is two of those boost converters that we just looked at. You can be able to see the first one quite easily. There's the transistor, there's the inductor, there's the input source, the diode and the output capacitor. So that there, that, and that is one of those boost converters. So what I can now do is I can pulse this transistor on and off. I can control the current in that inductor and push power into this output capacitance. Now, then you think, well, what's the other transistor and diode for? Well, that's when the voltage here goes negative, because I've got to do the rectification. So as long as I know whether I'm in the positive or negative half cycle, I can operate this first boost converter here in the positive half cycle. I can operate the second boost converter in the negative half cycle. And now, because I can control the duty cycle of those switches, I can control how much current flows in the harvester. And I can then get rectification through the action of this circuit. And I can control the current in the harvester at the same time. So I can maximize the power density of the harvester because I can control the current in the inductor, which means getting the correct force on the harvester to get the maximum power density on the mechanical system. Okay, so again, I know I'm going quite fast now, but I hope you start to see how some of this electronics we've just looked at and the capabilities of that starts to link through into be able to control the mechanics and maximize the power density of my entire system. One of the other nice things that you can do here, and this is very relevant, I think, to what we need to do thinking about the ENHANCE project, where we may well have systems that we want to tune to resonance, but the predominant frequency of excitation is maybe changing quite a lot as we operate a car, for instance, at different speeds. So we might want to be able to tune the resonant frequency. And people have looked at doing this by changing the tension on a cantilever, by having a cantilever which sort of bends up a little bit at the sides, changing the tension on it, changing the spring constant. Pretty difficult to change the mass, but people have looked at changing the spring constant to try and do frequency tuning. The nice thing, though, about putting power electronic circuits onto these sorts of systems is you have a whole lot of degrees of freedom as to what you can control electronically and how that reflects back in the mechanical domain. We've just talked about the fact that if I can control the current in an inductor using power electronics, effectively I can control the damping force in my harvester and optimize the operation of my harvester. Well, that force that I create in the harvester by controlling the electronics doesn't just have to be a damping force. If I set the phase of it properly, then it can be a spring force as well. And you can see this directly by we looked at earlier and you looked at yesterday, the basic model here of an electromagnetic harvester, in this case, put into an electrical system, coupled through a transducer with an electrical load on it. Normally, I'd only be talking about putting a resistive load on here. But if I put an inductor or a capacitor on here as well, those reactive components will get flipped through the transformer turns ratio of the transduction mechanism and will parallel up with the spring and the mass in the system. So by putting reactive elements here onto the output of one of these energy harvesters, I can actually tune its mechanical resonant frequency, which is quite cool. Now, of course, I don't really want to have to put on a bunch of different capacitors or a bunch of different inductors to try and tune the resonant frequency. What I'd like to be able to do is to, again, take my power electronics out and control the current in this device so that it mimics the current that would flow into a capacitor or an inductor, so that I can then control at will frequency of my harvester. And here's an example of how to do that. So here's my harvester model, transduction mechanism, the inductor, the harvester, and 4 switches here where, just like I had before, I can turn on this switch, and I can pull current in one direction. I can turn on this switch and pull current in the other direction through the harvester inductance itself. And as long as I put a current with the right amplitude and the right phase into that inductor, then that will reflect ultimately back through into the mechanical system, and I can effectively change the spring constant of my system through the action of this power electronics. We did that actually in a project actually that we were in with Paul Murrell actually, started in 2008 called MobiSense, and we had, the idea was to put these quite large harvester devices into a kayak which was going to go around and do water quality monitoring. And of course, depending on the frequency of oscillation of the boat that we were working with, depended very much on the sea conditions and the weight and everything, we wanted to be able to tune the resonant frequency. This is exactly the technique that we used there. You can see here that we, the EMF that we got from the transducer, the current that we put into the transducer, and we were able, and it's a fairly small change, I admit, but you can see here a change in resonant frequency. You can see as we put in, basically with the power electronics, we can emulate positive or negative capacitances. So we were able to add a positive capacitance to the system and decrease the resonant frequency a bit, or add a negative capacitance and increase the resonant frequency a bit. And okay, it's around a 10% change in resonant frequency here, which doesn't look very much when you're working at just 1 or 2 hertz. But if we can get a 10% change on something as we move into the kilohertz range, maybe that's quite a useful thing to be able to do in terms of tuning the behavior of this device. Okay, now, Osrina, am I okay to do about 10 more minutes on the piezo stuff? Because I think that's directly relevant. Okay, okay. Right, so specifically then talking about piezo circuit, interface circuits. So we're going to try and leverage a little bit of what we've just done in terms of the basics of power electronics. That means we're going to try and operate things in switch mode. We recognize, therefore, that whenever we transfer energy from one element to another, from one storage element to another, capacitance perhaps on the piezo, through to the energy storage element that we have in the system, we're going to have to do that through an inductor, otherwise we're going to have energy loss. So as I've said, you know, the basic operation for these sorts of circuits, bridge rectifier, lots of deficiencies with this, lots of losses in these diodes, difficult to achieve the right force that you want to achieve on the piezo device, and not a very optimal solution. Very simple, but not very optimal. I already talked about the ability for doing this charge flipping with this type of circuit. And if you remember, what I said was, as the piezo moves from its stationary position up to its most positive flex, this point here, I've got a voltage on the piezo which is trying to restore the beam into the neutral position. And instead of allowing that to happen, if when I get to this point here, the beam is in the upper position, I close this switch and flip the polarity of the charge on the beam. Suddenly then, rather than having the beam in this direction with a restoring force pulling it back to neutral, I've now got a force that's pushing it further in that direction. The electrostatic force on the piezo is pushing it further away from that position. So if I now push it down again, as I do when the mass moves, I can do even more work because the force that I'm working against is greater. So that's the basic principle as to why this charge flipping gets you more power than not doing the charge flipping. You get much higher voltages that you can see on the device than without it, and crucially, you have the polarity of that voltage in such a direction that it is working to give you a higher restraining force against the inertia that is pushing against that proof mass, which is exactly what you see here. So there's also another way of thinking about it, and certainly from a power electronics perspective, something that I think is quite useful. If you look at the input current that you see that is produced from the current source in the piezoelectric material, of course that gets integrated onto the capacitor of the device, and that is therefore the voltage that you would see on the capacitance of the device if you didn't change anything, if you just allow the piezo to wiggle up and down. If you put some of this charge in here, and here's an example where we just short the voltage to 0 rather than actually flipping it. This is what Michael and various others would call synchronous electric charge extraction. Then the voltage increases and gets pushed back to 0, increases and gets pushed back to 0. If you look at the fundamental component of this, so this clearly now has a bunch of harmonics present, but the fundamental component of this is now further shifted towards being in phase with the current. So what we'd like is to have voltage and current in phase. That's how we generate real power. If we're just putting that current into a capacitor and generating a voltage, then as you know, that's only a reactive power exchange. You get no real power just putting current in and out of a capacitor. But if you do this chopping of the waveform here, then you're actually changing the phase angle of the fundamental, and you're bringing the voltage and current to be further in phase with each other than being 90 degrees out of phase. And that gives you the ability to extract real power that you wouldn't have if they were perfectly out of phase. When you put a resistive load onto this harvester, then of course, again, you're pulling the voltage and current to be a bit more in phase. But by starting to chop the waveform like this, you get much better capability for pulling these things in phase. And as I mentioned to you in the last set of slides, when we do the charge flipping like this, then actually we turn what is a weakly coupled VDRG into a strongly coupled CDRG. So the way that we went about implementing this circuit, a little bit different to what Michael and his colleagues have done, was to create something using a stack of multiple transistors with an inductor here and the harvester in the middle. And this circuit now, you'll have seen a number of times in what I've presented on power electronics, having 4 transistors here. It's called an H-bridge, and it lets you connect between the 2 points here, lets you put a voltage on here which is positive in one direction or positive in the other direction. If I turn S1 and S4 on, I get a positive voltage on here with respect to here. If I turn S2 and S3 on, I get a positive voltage here with respect to here. It's a very simple circuit. It's used a lot for simple control of DC motors, so you can spin them in one direction or the other. Well, you know, that's a very useful thing to be able to do here with the harvester as well. So I close S1 and S4 in this case. I ring energy, therefore, through an inductor to try and minimize the losses onto the capacitance of the harvester itself. Then I open the 2 switches so that the harvester is in open circuit, and the harvester moves. It generates, therefore, an additional voltage internally because of the action of its own current source. I close the same 2 switches again because now the voltage on here, because of the movement of the device, is now in excess of the DC voltage that I primed the device with. That means that current actually flows back out of the device, back into the battery. I then open those 2 switches again, and I close the other 2 switches, and I do exactly the same thing in the opposite direction. And I get this sort of waveform. Pre-charge the piezoelectric material to a certain value, then allow it to move, and I see approximately a sinusoidal voltage while it moves. Then I discharge it again. So effectively, I'm borrowing a bit of energy here in order to get the right force on the device, optimize the mechanical coupling into the system. Then I allow it to move where it generates power, and then I take that energy and I put it back into the power supply. So I've got a fundamental difference here. I've got more energy to take out than the energy that I borrowed in the first place. And of course, this is like a V2 squared minus V1 squared. So if I just keep increasing those values, even if the difference between them is the same, I end up winning. So the amount that I generate here as I push the voltages up, even if that difference here is the same, the squared value of the difference between them is higher. And that corresponds to the fact that I'm putting more and more force onto the piezo. Of course, if I take the force to be too high, then I stop the piezo moving properly and I wouldn't generate power. So it comes back to the original analysis we did in the last set of slides on the Coulomb damped resonant generator of being able to create the right force, the optimal force to maximize the power density. There's a simple expression for the maximum amount of power that you can get from this circuit, crucially now dependent on the Q factor of the inductor and the piezoelectric capacitance. So using this type of circuit here, this type of circuit operation, when you're making your piezoelectric films, one of the things that you need to think about very carefully is that the resistance of those films needs to be as small as possible. So you may well be concerned with maximizing the electrical coupling, maximizing the capacitance. There's various things you might be interested in. Please keep in mind that the person who's designing the circuit to attach to your piezoelectric film is going to be very concerned with how high a Q factor they can get in a circuit that they attach to the piezoelectric material. And that's not just a function of the circuit, it's also a function of the piezoelectric material. If the series resistance of that piezo material is too high, we're limited on Q factor, and that will really limit the amount of power we can get out of this film. I showed you this diagram earlier where you can see the operation. You can see us pre-charging the system. We get the increase in voltage as the device moves, and then we take the energy out and we do another pre-charge. And we're able to get significantly more power with this technique. This is the power that you can get here with the bridge rectifier. This is the power that we can get here, this red line, with our technique practically. This dotted line here is the power that you can get using SSHI theoretical maximum, and this line here is the theoretical maximum that you get with this specific technique. I think I probably won't talk about the electrostatic harvesters. We've talked enough now about power electronics for harvesters, but essentially you see the same sorts of concepts coming up again and again. We're trying to control voltage to control force, or we're trying to control current in order to control force, depending on the type of harvester that we've got. And so we look to all of these different aspects of power electronics to be able to do this control in the electrical domain to actually influence what's happening in the mechanical domain to maximize the performance of these systems. And like I say, I'll skip these slides specifically on the electrostatic harvester. So just to conclude then, the harvester as a unit, just the piezoelectric material or the electromagnetic transducer or whatever type of harvester you're building is not useful in isolation. It's got to have the electronics attached to it to make it useful. And at a very basic principle, that means taking the AC and converting it into DC so you can power some load electronics. And if you can't do that, then the harvester is not useful to you in a system. In reality, then what we can do, though, is to start thinking about that electronics as not only something which is doing the basic AC to DC conversion requirement, we can think about it as something now that can really help to optimize the system. And we can control the current in the electromagnetic harvester or the voltage on the piezoelectric or electrostatic harvester to try and maximize the power density. So we look to produce these switch mode power conversion circuits that interface to our harvester that try and operate in as most efficient way possible so that the energy loss in the circuits is very small, but also at the same time that we enable circuits that can give us the maximum power density by optimizing the force on the transducer itself. Okay, I think that covers off everything that I probably should say, given that it's now getting a little bit late. So thank you very much for listening.